also link it to resources and explain related concepts. And I usually like to begin with slides. Why we uncertainty has all right, let's go ahead and get started. So I'm not Dr. O'Day, you haven't figured that out. If you're confused about that, there's not much I can teach you about circuits because you have much more basic problems. But I've been teaching, as I think many of you know, circuits 1 this semester, and having a lot of fun doing that. And I wanted to, Dr. O'Day had to be out of town today, so I was really looking forward to the chance to come in and give you guys a lecture. So let's talk a little bit today about three-phase power. We're going to focus on power relationships and power vector corrections today. So this is a slide you may have seen in one of your previous lectures. It's the fundamentals of three-phase power. Why is it advantageous? So when do we use three-phase power? Why are we teaching you three-phase power? Where will you encounter three-phase power? House. Not your house. What will you encounter at your house? That's a good two-phase, right? Mm-hmm. We'll talk about that today. Where will you see three-phase power? Transmission, power transmission. And why do we use three-phase power transmission? I'm pretty sure Dr. O'Day covered that.
It's like a steady source of power.
Excellent. It's constant power, right? Excellent. That's very good. So we have the voltage between A, B, or C and ground, or neutral, are shifted by 120 degrees, right? We have each of the wires. Yes, you're in the right place. We will have a quiz, by the way, at the end of class. I think you might know about that, right?
Subtle.
I'll leave 10 minutes. Quite yet. What's the quiz on? Electrical engineering. If I tell you that, you're going to be worrying about that all lecture. Well, it's a problem you see in the lecture. Maybe last 1 or 2 classes ago. So, excellent comment about the power being constant. One of the reason we use three-phase is we want to achieve the situation where the instantaneous power is constant. That's comes about because of the way we phase the signals. We could use 6 phases. We could use 12 phases. We could use 4 phases. Why do we use 3 phases? 21. That's what the separation has to be for 3 phases. But we could use 4 phases and separate them by 360 divided by 4, which I think is 90, right? Mm-hmm. Why not use 6 phases? More is better. That's always engineering, right? Why do we only use 2 phases at your house?
Double the power.
Because at your house, so your house is what's called when power that comes to your house is a 3-wire circuit that has essentially 120 volts between A and ground and B and ground, and A and B are shifted by 180 degrees. And why is that done?
Double the power, double the voltage.
Why do we want to double the voltage?
Like power higher, power.
Right, so we want to be able to make a 240 volt signal at your house because some equipment, like your air conditioner, your electric dryer, your electric heating system, work better at higher powers. And you'll learn about that when you get into power class. Why not run 3-phase to your house? Actually, I used to live on a farm. They ran 3-phase from the street to the transformer outside my house because it was a quarter mile from the road to my house. So voltage didn't run three-phase on my property. In what sense? Not so much power, but it would just take another wire. And power distribution cables are expensive, especially when you talk about high voltage transmission. So three-phase was chosen rather than 4, 5, or 6 because it accomplishes what we need, which is the constant power, but it's done with the minimum number of wires. The decision to not do that to the house, I suppose, was an economic decision. That why run 3 wires to your house when you can get away with running 2 wires to your house, 2 plus ground. So in this, you've also, I think, learned about Y and delta configurations, and we're going to make use of that today. So I quickly wanted to review those. That when we have things in a Y and delta configuration, we can talk about the line voltage. We can talk about 2 quantities that we often talk about are the phase voltage and the line voltage. The phase voltage is the voltage between A and ground, B and ground, or C and ground, and we call that V sub T. The line voltage is what you measure when you put a meter across A and B, or A and C, or B and C. And these 2 are related by the square root of 3. And I believe you probably derived that in one of your previous lectures. So there's going to be a lot of square roots of 3 floating around, and we'll have to keep track of those. So it's sort of a summary of the line of the various quantities in terms of line voltage and phase voltage. And if you want to, I don't know if you're using these same slides I am. Most of these slides come from the textbook, but I can, if you want access to the slides, send me a note and I can give you access to the slides. Now the other thing we will make use of today is the power relationships. So you've talked about active and reactive power, right? Or you might remember that from Circuits 1 if you talked about that in Circuits 1. When you were learning DC circuit analysis, life was easy, right? How did you calculate power being dissipated in a resistor? How did you know a resistor was dissipating power? Let's start with really basic things.
Current.
They're hot. Thank you. Very good. You touch it, it's hot. It's warm. That means current has to be flowing. It's dissipating power. How much power is it dissipating? Current times voltage. That was easy, right? V times I. Life was good. We get to AC circuits. We talk about inductors and capacitors. Power became more complicated. We have real power, or active power, and reactive power. Does a capacitor or an inductor does an ideal capacitor or inductor dissipate power? No. So why do we worry about inductors and capacitors? Who worries about reactive power? But okay, so who worries about it?
Could be the power company.
Why do the power companies worry about reactive power? Well, you're all on top of everything here. What about power factor? Very good.
Mm-hmm.
When the power company worries about power factor, because that controls, what does that control about power distribution? The losses. Very good. That controls how much money they're going to lose trying to get that power to your house. And hopefully you've seen it. I don't know if you did that in this class or in Circuits 1, but you've seen the derivation of that. We'll touch on that if we have time later today. So we have this real and this active and reactive power, and they're related by cosine and sine. But we also have this relationship between line current and phase current, and phase voltage and line voltage. So we can compute power as V times I sub L over the square root of 3, just using this relationship. And similarly, we can compute the reactive power in the same way. And we can also talk about the total power being delivered by these 3 wires as being 3 times the power coming on one of the faces, because it's a balanced condition. all the impedances across the different wires are equal. So we have the total power delivered into the three-wire system is the square root of 3 V sub L times I sub L times cosine theta. And similarly, the reactive power is the same thing times the sine of theta. So we're going to talk in a little bit about power factor correction. And the magnitude of the complex power is the sum of the squares, the magnitude of this E squared plus Q squared, and that's just the square root of 3 times V sub L and I sub L. And the angle of that power is equal to theta, which is what we call the power factor. So we have, let me skip the slide and go to the next one. This sort of rehashes the summary that we just went through. So let's work a simple example. We have a line voltage of 208 volts RMS. We have a total power of that we want dissipated in the system is 1,200 watts. And we have a power factor of 20%, 20 degrees lagging. And we want to determine the magnitude of the line currents and the value of the load impedance per phase in the delta. Okay, so we can put to use some of these expressions we just described. I often like to talk about the fact that, only in courses do you get these fictitious homework problems where they give you some information and they tell you to calculate some other information. A lot of these problems are not really what you'll use this stuff for. In a moment, we'll work a problem where you actually worry about power distribution. And then it'll be, I think, clearer why we need to talk about some of these quantities. This is just sort of a made-up problem to teach you the relationship between the different quantities. So the total power, we said, was square root of 3 V sub L, I sub L times cosine of theta. This is the active component of the power. This is the reactive component of the power. And the only difference between these is cosine and sine because P and Q are at 90 degrees from each other. And if we talk about per phase, we can take the total power divided by 3 and write this expression per phase. The square root of 3 divided by 3 is just 1 over the square root of 3. So from this, since we know the line voltage and we know the power factor, we can compute the line current. So to achieve that line voltage and that power dissipation through this system, this is what the line current has to be. Just a simple calculation. This is known, that's unknown. And we can also talk about the current. Since we know the line current, we can also compute the current that would be flowing through one of these components, which we call the delta current. And that's just going to be this current divided by the square root of 3. So the current flowing through one of these impedances is 2.05 amps RMS. So that means that the magnitude of the impedance, we can now take the line voltage divided by the delta current, and that has to be then the magnitude of the impedance of those loads. And since the power factor is 20 degrees, we now know the magnitude of the impedance, and we also know the power factor angle. So we now have a complete specification for the impedance. So the impedance in this network must be 101 ohms at an angle of 20 degrees if we're to achieve that line voltage, that power dissipation, and that power factor angle. So this is a simple type of homework problem calculation. Now, why do you need to be able to do this calculation? Well, if you were a power distribution engineer and you were trying to sign up a big customer like a manufacturing plant, you're going to want to be able to you're actually going to want to be able to tell them what their power factor must be so that you can achieve a certain efficiency of transmission. So you'll do this calculation because you're going to be able to tell them, if I'm going to deliver to you power at a certain power factor, like 0.9, this is what the impedance of your manufacturing plant must look like. And they may say, well, it doesn't look anything like that because we're using this type of machinery. And then you say, okay, well, what we're going to have to do is figure out a way to make your impedance look like this so we can get our 0.9 power factor. So everything really does revolve around the power factor when you do these kinds of power distribution calculations. And we'll work a more concrete example of that in a moment. So here's a second example where we'll look at a balanced Y circuit, and we're going to determine the real and reactive power per phase of the load and a few related quantities. So here we have a generator, and we're looking essentially at one phase of the system. We have a line impedance. This can represent the impedance of your cable, for example. And then we have a load. We have a Y connection, but we're just looking at one leg of the Y connection, which has an impedance of 20 ohms plus J10 ohms. And then the question is, can we calculate things like the real and reactive power per phase of the load and related quantities? These impedances of your cable may seem small. When you buy a cable, they say like 0.1 ohm per foot. And you don't think anything of that, right? 0.1 ohm, I can live without that, right? But if you remember, when you're transmitting over hundreds of miles, 0.1 ohm starts to add up. And when you're transmitting at 1 million volts, or 1 million amps, or 100,000 amps, that starts to add up in terms of power losses. So you can get these quantities, you can actually find these, if you've ever purchased cable, if you go to a cable catalog, you have all the different cables spec'd out in terms of things like those impedances and such. And real-world cables do have inductance as well as impedance. Why does a real-world cable have inductance?
Because there's going to be a magnetic field around the cable whenever there's current traveling in the wire.
And what's an example of a cable that might have more inductance than less inductance? Red wire. Very good. It's wound, right?
Mm-hmm.
And anytime you have a winding going through a magnetic field, you create inductance. Mm-hmm. So inductance can arise in places you may not think. And you've talked about mutual inductance, I think, in one of you by now, either in this class or previous class. And the other side of this is whenever you have a coil in a magnetic field, you get an induced current. So if you've ever run speaker wires a really long distance, they turn out to be really good antennas, right? And you can often pick up local radio stations and things without much trouble. And that's because you're creating it's got inductance, and therefore you're getting induced currents and such. So we have this one leg of a Y circuit. We have a line impedance, and let's see what we can do in the way of calculating some voltages and currents. So the voltage between A and neutral, we said was 120, and we'll establish a reference of 0 for that for this one phase of a three-phase system. And the impedance, the total impedance across that voltage is the sum of these two impedances. So that's going to be 1 plus 20, which is 21, and 1 plus 10, which is 11. So the current being supplied, this current here, is just going to be V over C. And assuming you can do the complex numbers, I hope you're using MATLAB or your calculators to do complex number calculations. what we get for the current. 5 amps at an angle of minus 27 degrees. Now, knowing that the current, we can calculate the, and the voltage and current are related, as was said by that simple calculation. So, so the voltage, now that we know the current flowing through here, the voltage between here and here is just going to be the current times this impedance. So we have the current times the impedance to give us the voltage. And that'll turn out to be 113 volts at an angle of minus 1. So now that we have the voltage and the current flowing here, we can actually compute the power. We can take V times I for the instantaneous power, and that's just going to give us that quantity shown. And this is in polar notation. If we write that in rectangular notation, we can identify then the active component of that power and the reactive component of that power. So we started with the voltage, we got the current, we got the voltage here, we used the voltage and the current here to get the power. And now we can compute the source power per phase, which is just going to be the voltage here times the current here. So this represents the voltage here. This represents the power here. This represents the power here. So we take 120 times the current. And again, if we write that in rectangular notation, we've got the active component of the power and the reactive component of the power. And since this is per phase, the total power is going to be 3 times that. And therefore, the total source power is going to be the sum of those two as complex numbers, and the magnitude of that source power will be the magnitude of that complex number. So, what we've done here is go through some simple calculations of how we can get voltages and currents and powers. Now, as a power distribution engineer, what parts of this problem are you going to be worried about? So, this is just the gymnastics of showing you how we can compute voltages and currents and things. The more important question is why do we want those things? What are you going to be worried about? If this represents your manufacturing plant, this represents your transmission cable, this represents your source, what aspects of these calculations are going to cause you to lose some sleep?
How much reactive power you have?
Reactive power, right. You're going to worry about, for example, the power factor at the load. You're going to worry about how much power is being consumed in the lines. You're going to be worried about the power factor, so you can. What would be the ideal case if you could achieve that? Resistant, right? Which means these power quantities would be, P would be what? Some number, and what about Q? Q would be 0. So how are we going to improve power factor? How are we going to make power transmission more efficient? We're going to try to get rid of Q. We're going to try to reduce that. So here we have a three-phase distribution system. We have a power plant somewhere. We were talking in the previous class about this. One of the complicating factors here is nobody wants to live near a power plant, right? So you don't just put a power plant in your neighborhood. Nobody wants to live underneath high voltage power lines anymore, right? Because you've all seen 60 Minutes and where they claim that, news segments like that where they claim living under power lines is not a good thing for your children. But we all want to consume power and don't want to pay a lot for it, right? So as customers, we worry when your power bill gets really high. So it's like set up for totally the wrong situation. The best situation would be you live next to the power plant, you plug right into the power plant, and everything's fine. So we have to worry about all this stuff. So we start with a power factor without these capacitors. We just have the basic transmission system. We start with a power factor, and the question we'll ask is how can we improve that? So I'll sort of step you through the process, and then we'll work an example. So what we're going to try to do is to modify the reactive component of this power. The relationship between the reactance of that impedance that we're going to add and the capacitance is minus omega CV squared. I don't know if you've derived this or not, but just take this on faith for now. We can go back and derive it later. But this expresses the reactance of the impedance. If you recall, the impedance of a capacitor is 1 over j omega c. So that's one of the reasons why it's negative, because you have 1 over j and you have omega, and this relates to the energy storage in the capacitor. And we know that complex power is related to P plus JQ. We can write that in terms of cosines and sines of the angle. And the power factor is defined as just cosine and theta. So when I give you the power factor, you can compute the theta. So with all this information, we can actually do design of these networks. Yeah.
How's the quiz going to be on?
No. The quiz is on something you saw, I think, probably last class. It's simply it is. The quiz is on a Y network, though. I'll give you that hint. So, but if you start thumbing through your books on Y networks, we've got a few more minutes yet. So the P, if we know S, we can figure out how much of that is P and how much of that is Q based on the angle. And we can actually write a few trig relations between power factor and cosine. That allows us to get a relationship between sine and power factor and tangent and power factor. And we'll make use of these equations shortly. So these are all the equations we'll need to do the power distribution problem here. So let's look at a specific case. So we have 60 hertz frequency. If this were Japan, what would that frequency be?
50 hertz.
If this were Europe, what would the line voltage at our house be?
220.
Yeah. And in the U.S. it's 120. So 60 hertz. Our line volt, we want to achieve a line voltage of 34.5 kilovolts, and we want the power factor to be 0.94. That's our goal. Those are our goals. However, when this manufacturing plant comes online, we discover that the power factor is 0.78. The plant tells us they need 24 megawatts. That's what we have to deliver to the plant. If we have to deliver 24 megawatts here, how much are we going to have to generate here?
20.
What? More than 24.
More than 20.
And what causes our stock price to go down? The amount of that, the difference between this number and this number, right? Which is presumably going to be burned up here. So we have to worry about we'd like to make this as efficient as possible, maximum power transfer. So just repeat some of the key equations that we'll make use of. I'll point these out as we go through them. So let's first start with the power factor. We have a power factor of 0.78. So we can compute the angle that corresponds to that power factor. And then from that we can compute the sine of that angle. We'll need this to deal with the reactive component of the power. So if the power factor is 0.78, the sine of theta is going to be 0.626, just a basic trig property. So if sine of theta is 0.626, then the reactive component of that power is going to be our 24 megawatts times sine of theta, or 15 megawatts. The active component of the power is going to be 18.7 megawatts, 24 times cosine of theta. That shows you directly how the power factor plays into these calculations. So we have our old power, 18.7. Now we want to get the power factor to be 0.94. So that means that our new Q is going to have to be minus 6.8. That's just, if we take this power factor and this power factor, this power, this active power, and we compute Q from that, we get minus 6.8 megawatts. That means we have to somehow go from 15 megawatts to minus 6.8 megawatts, which means we need to somehow dump another minus 21 megawatts into this system of reactive power. And again, think about that. This isn't like resistive heat. This is just reactive power, but it's influencing the overall efficiency. So, fortunately, this is negative, which means we can use capacitors to achieve this. If that were positive, what are we going to have to add to the network to correct this? Inductors. Why is the power factor correction typically negative? That's not by chance. That most of the time we're adding capacitors. Why? What's causing this power factor disparity?
Motors?
Motors. Inductive devices, motors tend to be inductive. They're coils of wire. So most manufacturing plants or any kind of large installation appears as an inductive load because of all those motors. So we've got to add this minus 21.8 megawatts of reactive power. We can divide that by 3 and get minus 7 megawatts per capacitor. And if we're going to use a Y, we have a Y connection here. We know we have the line voltage. We can compute the voltage across each capacitor, what we call the phase voltage, using our relationship between the line voltage and the square root of 3. We have now the Q. We have the frequency. We have the Q. We have the voltage, so we can compute the capacitance. So we have to add 48 microfarads per capacitor, 3 48 microfarad capacitors, and we can increase the power factor from 0.78 to 0.94. So what's that going to cost us? Who pays for this? How about the back of the room back there that's been quiet all class? So So what have we just done? Summarize for me what we've just done. How about that corner? What was the objective of this problem? I used to sit in the back, so I know why people sit in the back of the class. So I always pick on people in the back. What was the point of this problem? Real world problem. What? Correcting power factor. Why do we want to correct power factor? Well, that depends on who we are. If we're the power company, it's because we don't want to lose money generating power that's not going to be received by the customer. That's lost money, that's lost revenue. What's the customer's incentive? Is there a customer incentive? Well, let's think about that. So I'm a power company. Can I force this customer to put capacitors in their factory? How am I going to induce this? I'm going to come to the company and I'm going to say, look, I'll give you one of two options. You buy these capacitors and install them, or I charge you a higher power rate. So what's the missing piece of this to make this truly a real-world problem? So now you're the customer, and if you ever did work as a plant manager or an electrical engineer responsible for this, when I was in elementary school, my dad, who used to run a drugstore, actually came to me with a problem like this. I didn't know. The company had approached him and said, we can save you money by increasing it. I didn't know it was power factor at the time, but eventually came to understand that. They had to do with their refrigerators. He used to run a drugstore, and they had freezers and things running, and they had ways to offset those costs. From a customer point of view, you have two alternatives: buy the capacitors, or watch the power company raise your rates. How are you going to make that decision? I'll put in my little plug here for senior things like senior design.
Cost benefit analysis.
Return on investment, right? You're going to have to look at what's it going to cost to buy these capacitors, and over what period of time are they going to pay themselves off? It turns out, most of the time, these will pay themselves off within about a year. The payoff is very high on these. This is a no-brainer, and that's why everyone does it. And I think there's a slide, later in this lecture, there's a slide that talks about that. This is actually an example of efficiency as a function of power factor, and it shows you that as the power factor gets close to 1, you really do get a big benefit analysis. The benefits become really significant. So this, maybe we'll go through next class, but you can actually look at the cost of capacitors and such, and usually with these kinds of situations, because electricity is so expensive, and believe me, you all are going to be worrying about electricity in your lifetime, whether you're residential or industrial or both. Your electric bill every month as a business is a big issue these days. But usually these capacitors will pay themselves off within a year. It's a no-brainer type investment.
If you continue to add equipment, would you have to then add more?
Yes. As and this is not a static thing. I mean, as you shut some equipment off, like if you run equipment only certain times of the day, you will actually change your power factor. So another thing that's often done is to try to run your heavy equipment at night when power rates are lower. This is another game that's played. And these capacitors are storing energy which can be used at other times of the day. So they're actually nice from an energy storage point of view as well. So that's another thing that most manufacturing institutions will do, is they actually look at ways to run their heavy equipment at times of the day when electricity is very inexpensive, less expensive, like in the evening. Okay, so we have a 10-minute quiz. So are these